Hi, in this lesson, we're going to discuss decay. And decay, the formula is going to be very similar to what we did in 3.3. The only difference is, okay, this is going to be your final outcome, your final amount, whatever you want to call it, the final amount. This is your initial amount. E is part of the formula. And instead of having K, because it's decay, it's decreasing. So it's decreasing or decomposing or decaying. We're going to use a negative K. And remember, K is our rate. K is the rate, in this case, the rate of decay or rate of decrease. And T is going to be the time that it takes. E is, of course, constant, E, constant. And I'm out of ink. And PO is the initial amount. And PT is kind of the final amount. So that's kind of what these stand for, okay? So we don't want to make it all complicated. So in your book, they have, I think, where you have strontium 90. And it has a decay rate of 2.8% per year. So we know that that's actually going to be 0.0. This is going to give us K, and K is going to be a negative because it's decaying, 0.028. And that's what we're going to use for our value of K in our problem. Okay. And that's basically the information they initially give us, that we have some strontium 90, it's decaying at 2.8% per year. So first of all, we want to write our initial function. Our initial function is nothing real fancy. It's just going to be the final outcome. And in the book, they use an N, but I'm going to just use T, equals the initial amount times E times a negative K, when K we know is going to be now a negative 0.028. We're going to use a negative amount here, and times T. So that's our initial formula. That's basically what they were asking for. It says find the function that satisfies this at T equals 0. In other words, at your initial amount, T equals 0. This is the formula we're going to use. This is the amount we want to get back at the end. All right, so the second part of this problem is, suppose that 1,000 grams is present at the initial amount, 0. How much will remain after 70 years? Okay, so we're trying to figure out how much is going to be left after 70 years. We're going to start out with 1,000 grams. We could put the grams in. I'm not going to put it in. E to the negative 0.028. And we want to find out how much is left after 70 years of time. So that's what we're trying to figure out. P after 70 years. Okay. So all we got to do is put this in our calculator and figure it out. We don't have to do anything real fancy. Just 1,000 times E. And we just put in our E, second ln. And slide that over so we can see it. Second ln. You see this okay? It shows it better on the white, doesn't it? Trying to figure out where to put this so I can see it. Here we go. Second ln. Where's second? Here we go. Okay, there's, no, we don't want to do that. Screw this out. 1,000 second ln. There we go. Must have hit something wrong. To the negative, we're going to use this negative key down here. Maybe I can put this up just a little bit higher and you can see it. Negative 0.028 times 70. Negative 0.028 times 70. Parentheses. Hopefully I can't even find parentheses equals. I'm sorry. So that would be 140.86 grams. So after 70 years, we still have 140 grams left. And so that's our answer to it. All right. The next question we have here is how long will the half-life of 1,000 grams remain? How long does it take, in other words, to get, we call this a half-life. Half the life is going to be gone. So we want to figure out how long it's going to take for half of this material to decompose. And that's what we're kind of concerned with, half of the life of this material. How long is that going to take? So again, we're going to use our initial formula. Let's start out with our initial formula. Negative 0.028 T. And we're going to try to find out what T is this time, the half-life. That's what we're looking for right there. We're going to try to find that T. So half of there's 1,000 grams of material. Half of that would be 500. We want to find out how long it takes us for 500 to remain out of the 1,000. That's all they're asking for. Half of that 1,000. E to the negative 0.028 T. So the first thing we're going to divide by both sides by is 1,000. And of course, that's going to give us 0.5 equals. I'm going to write the E right here to save a little bit of time, negative 0.028 T, like that. Then what I'm going to do is I'm going to take the natural log of both sides. Just like we did before. And that causes this to go in front. Okay? And we know the natural log of 1, and the natural log of E is 1. Okay? So this just becomes a 1. So we have ln 0.5 equals negative 0.028 T. So we're going to divide by the negative 0.028, or we could even just divide by a positive. It won't make that much. And this should give us how many years it took to decay down to 500. So it's going to be a negative number because we're decaying. So we're going to just put in ln 5 divided by a negative 0.028. Hopefully we did it right. And I think I got a little mistake. And 0.5, yes. Makes a little bit of a difference. I would say second insert. Let's see if I get the 0.5 in there. Let's try that again. Okay, 24.75, so about 25 years. It takes about 25 years for this to get to its half-life. So half of the material will be destroyed in about 25 years. So we could have done, I did it a little differently from the book. I could have done it a little bit more formal. If I had done a little bit more formal, I probably would have come up with this formula, but it's kind of the same formula we use for, remember the formula for double life? Double. Well, this is the same thing. How long does it take something to double? It's pretty much the same formula for how much time does it take for it to get to half. It's the same formula. K is our constant. This would indicate how long it takes us. K times T equals ln2 is really what our formula is. If we want to find the time that it takes to get to the half-life, then it would be ln2 divided by our constant, our rate. This is the rate of decay. If we want to find the rate of decay, and of course this is the time to get to half-life, a little scribbly there, time to get to half-life. If we want to find, if we know the time, and now we want to figure out what's the rate of decay, well, that would be ln2 divided by the time. So it's basically the same as the doubling time, basically the same formula to get to half-life. Half-life, double time, basically the same formula. So pretty easy to do. And I did mine a little bit different than the book did. They got a little bit more formal than I did, but that's okay. Let's try another one here. Flip this over. Okay. So on the second problem, I had worked these out just to make sure I won't make a mistake. And I think that's the same problem I just did. What's this one? Following the birth of their grandchild. Well, that's example 4. Did I skip over some? I flipped the page here. Example 1. Oh, I flipped a couple pages. Okay. Let's look at example 2. Okay, plutonium-239. A common byproduct of a nuclear reactor. Okay. Can be very deadly, obviously, if people are exposed to it. And we want to try to figure out what's the half-life of this plutonium $239. So the half-life would be, well, let's just, and what do we want to find out? We know the decay rate, so we want to figure out how much time it takes to get to the half-life. Time to half-life. Okay, how much time does it take to get to the half-life? The time is equal to ln2 divided by k. And we know k right here, it says the rate of decay of this thing, which is our rate, is 0.0028%. But that's not k. K has to be as a decimal. So k is equal to, we still have to move 2 more places, 0.000028. So you can see the rate of decay is extremely slow, isn't it? It's less than 1% per year. I mean, it's very, very slow decay rate. So the time it's going to take to get to its half-life is ln2 divided by 0.00028. So let's see what that comes out to be. Let's clear this calculator, turn it on, clear it out. ln2 divided by 0.00028. Bingo. Is that right? 24,755 years, approximately. Almost 25,000 years. We'll be long gone before this even gets to its half-life, depending on how much plutonium we're using. So kind of a dangerous substance, huh? And that's why people are kind of afraid of nuclear reactors, because it takes so long. That's only half the life to decay, and then we still have another half-life to go. So probably talking 50,000 years for this to totally disintegrate or come very close to being unharmful. Okay, the last one we're going to do, which is really confusing here, but we'll try to give it a shot. It says sometimes we use carbon dating. You probably heard of carbon-14 dating to determine how old something is. So it says the radioactive carbon-14 has a half-life. This is example 3. So it's example 2. It has a half-life of 5,730 years. And they're examining these dead sea scrolls, and they realize they've lost, when they did some tests on it, they've already lost 22.3% of carbon-14. So they've already lost 23.2%. So we're trying to figure out how old is this scroll. So kind of a difficult problem, huh? So the first thing we want to do is figure out what our rate of decay is. What is our rate of decay? So the rate of decay is K, and K is equal to ln divided by 2. ln2 divided by T, time. So we know the half-life is 5,380. So K equals ln2 divided by 5,730. And this will give us our rate of decay. So let's see where that comes out to be. Our rate of decay is ln2 divided by 5,730. Pretty small number, 0.000. Make sure you get those zeros. Let's call it just 1, 2. And we'll put down the whole thing, 968. Okay, so that's our rate of decay right there. We know the rate to get to a half-life. That's the rate of decay, decomposition. Okay, so our general formula is PT equals PO, initial, times E to this number right here. This is not a percent, so we can just write it down, 0.001200968 times T. Okay. So 22% of this rate is gone. So what we're trying to get to is 100%, but this would be 100%, but we're already showing decay. So we're going to subtract the 22.3 from 100%. And that comes out to 77.7%, which we're going to change. We could either leave it that way and change PO to 100%. This is our initial amount was 100%, and this was 77.7 is what our final outcome is going to be. But we're going to change them to decimals because that way we can write this as a 1. 100% as a decimal would be 1. 77.7% would be 0.777. So we're going to write this as 0.777 equals 1 times E to this 0.000120968 T. And remember, what we're trying to find here is the time. We're looking for this t right there. That's what we're trying to find. Okay, so this was 100%. This is what it did is it decayed down to, we have 0.777 left. 77% is left. This is how much is decayed off. So we had 100%, we're down to 77%. So now what we're going to do, and this should be a negative because it's decaying. Okay, so what we're going to do is take the natural log of both sides. And if we take the natural log of this, it's just going to be 1. So that's not really going to help us. The natural log of E is 1. Well, I just go ahead and write it. The natural log of 1E. And then we can put this in front. I just write it as 0.00012t, just to make it a little bit easier. And this part right here will become just simply a 1. The natural log of 1e is 1. So then we're going to divide both sides by that constant. I'll put it down here, the whole thing, 0.001200968. And this should tell us how much is left. It'll be a negative answer, which means it's decaying. So let's find out how old this dead scroll is. ln 0.777 divided by, and 0.00, we're trying to find exactly how old it is, or as close as we can get. 968. So it's approximately a negative 2085.79. So let's round that off. It's about 2,086 years old, this Dead Sea Scroll. Well, I was doing some figuring. Okay, I don't know if I'm totally accurate, but the year is 2020, right? So apparently this was written about 46 AD. This scroll, you can kind of figure it was written about 46 AD. The year 0 began with the birth of Christ, right? So Christ died when he was 33. So this had to be written about 13 years after the death of Christ, is what I figure. Is that when this scroll was written. So fairly much after the death of Christ, these Dead Sea Scrolls were written. So they're probably a pretty accurate account of the situation at the time. So that's pretty much how we're going to do it. If you want to really get confused, you can try this example 6, but that's kind of how we do this. So to figure out how old this scroll is, the first thing we had to do is find out what is the rate of decay. And that's what we found here. We tried to find a rate of decay. And once we found that rate of decay, then we were put this in. It was a little confusing with this 22.3. What was left is about 77% of the scroll is still left. The carbon is left out of 100%. So you can think of this as 77% out of 100%. We changed it to a decimal because it's easier to work with 1 than it would be with 100. And then instead, we could have done this with 77 and 100. It just makes the computation a little faster to change this to a 1. We realize if we take the natural log of both sides, the E kind of cancels off. So the reason we did these problems is to kind of give you an idea how we can use E we're not really doing anything with taking derivatives or anything like this. We were just kind of working on trying to figure out what is this constant E? Where is it used? And it's used for continuous growth, continuous rate of growth or continuous decay of growth. That's where we use E most likely. We can use it also in a couple other things, but it's always kind of can be used, and we can see how it comes up in different formulas. So it's kind of interesting to use. So I hope you enjoyed this little video. Try the problems you have, see what you can do.